All right, we'll assume that's a yes. So today we'll be continuing going on with our chemistry, and today we're starting a new chapter. So this is chapter 4, and chapter 4 is going to be all about solutions. So maybe I'll just write that down. So chapter 4 is going to be all about solutions. And so solutions mean something dissolved in water. We're going to have some sort of a chemical, and it's going to be in like a dry form or on its own, and we're going to mix it with water. And so in this chapter, we're going to talk a lot about acids and bases and molarity and concentration and titration. So I'm not sure if any of that is familiar to you. It certainly wasn't to me when I came into college. So let's go ahead and get started. Before I forget though, if you guys could, as always, put your net ID in the chat, or your Iowa State email in the chat as we get started, so I can record attendance. And then lastly, before we start, what questions do you have for me? Okay, so let's get started then. So number one, what is the equation for molarity? And more generally, what is molarity? So molarity is a measure of concentration of a solution. Solution. So if something's really concentrated, it has a lot of whatever chemical dissolved in it. And if it's not very concentrated, then it has a low molarity. You can think of it like maybe you're making Kool-Aid and you're measuring the molarity of the sugar in there. If it was a lot of sugar in your Kool-Aid, it would be a high concentration or a high molarity. Or low molarity would mean you didn't put much sugar in it and it's really watery. So the equation for molarity is capital M, which stands for molarity, is the moles of your solute divided by the liters of solution. So this is liters. And then this is moles of your substance. Divided by, so moles of your substance divided by the total liters of the solution that you're making. What else did I want? I think that, yeah. So the one thing to keep in mind here is that when people talk about concentration, what they're talking about molarity. These terms are more or less interchangeable for this course. So if they're saying, what is the concentration? What they want is they want molarity. So number 2 is an example problem. Number 2 says, what is the molarity of a solution containing 12.5 grams of sodium chromate in enough water to make 750 milliliters of solution? Well, we have the liters right here, 750 milliliters, and we have the grams, but we don't want grams, we want moles. So let's take our 12.5 grams of sodium carbonate. So this is sodium chromate, is Na2CrO4. So Na2CrO4, and we have 12.5 grams of this. And our equation here wants moles, it doesn't want grams. So how do we get from grams to moles? Let's do the same thing that we were doing in last chapter. So 1 mole of sodium chromate is going to be how many grams? Well, we're going to look up the molar mass for sodium chromate, Na2CrO4. I kind of butchered this. I'll rewrite it. So Na2CrO4. So the molar mass for Na2CrO4, that would be 161.97 grams per mole. And that's just from the periodic table like we did last chapter. So I'm going to take that and put that on the bottom here. So 161.97 grams of sodium chromate. So this will give us 12.5 divided by 161. That gives 0.07717 moles. It's a 7 there. So now, okay, so we have our moles, and our equation calls for liters. Well, our problem gives us 750 milliliters, so we have to convert milliliters to liters. So let's do this. Now you're going to get really fast with the milliliter conversions, and the conversion is just like a millimeter or a milligram. It's 1,000 milliliters per liter. So that gives you 0.750 liters. So we have our moles now, we have our liters. Now we want to do is find the molarity, or find the concentration. So that would be the moles, 0.02717 moles, divided by the liters, 0.750. And that will give you a molarity of 0.103. And that would be your final answer. You would say that this solution has a molarity of 0.103. What questions do you have on number 1 or number 2?
So are the units for molarity just moles per liter? And do you need to specify that, or is it kind of just understood?
Yeah, you know, great question, Megan. It's kind of just understood implicitly, but what you can do, I know this is weird, it's this M equals 1.03. Sometimes the unit they just put is a capital M. And what you understand when someone writes 0.103 M, that means moles per liter. So just write this capital M after your answer. Does that make sense, Megan?
Yeah, it does. Thank you.
Okay. So we'll get some more practice with this notation. All right, so let's move on to, let's use our molarity in another type of question that you often get, which is a dilution equation. Now, does anyone want to explain in their mind or have a good explanation of how to explain what is dilution? Does anyone want to give that a shot? So dilution, in my words, would be adding water to make something less concentrated. That might seem really basic, but we use it the same way in real life, in everyday conversation as we do in chemistry. So you're taking something that's concentrated, and we're just going to add water to it, and that's going to make it overall less concentrated. You can think about, again, like you had Kool-Aid, and you just add a bunch of water. It's not going to be very tasty anymore. That's because it's not as concentrated. Now, the equation we use for dilution is M1 V1 equals M2 V2, where M is going to be the molarity and V is going to be the volume. So you're taking some amount of, let's call it your Kool-Aid. You have a certain concentration of your Kool-Aid, a certain volume, and then you're going to add water to that Kool-Aid, and then you're going to have, because you added water, the volume is going to increase, but your molarity is also going to change. Now we can find the relationship between the volumes and the molarities using this equation. Now the ones and the twos just mean that one is the initial, what you're starting with, and two is your final, what you're finishing with. So why don't we use this on number 4, and I'm going to write down the equation, and I'll give you a couple minutes to try to work through number 4 on your own. So we're just going to use the dilution equation. And why don't we spend a minute or two and try to figure out where you put all the variables in number 4. Okay, so maybe you've had a chance to look at this one. Now the dilution equations are, the dilution problems are almost always going to be the same. And really it's just a challenge of figuring out what the problem statement says. So let's see, we have a stock solution of 6.5 molar ammonia. Now notice this equation here doesn't, it doesn't have anything to do with the type of chemical. It has nothing to do with moles or grams. So this ammonia piece is more or less unnecessary. So we have 6.5 molar, and you take 15.5 milliliters, and we're diluting it to 300 milliliters. What is the final concentration? So let's write down what we know here. So we have 6.5 molar for the initial molar, and the initial volume is 15.5 milliliters. Now the final concentration is what we're looking for. So that is just M2. That's what we want to find. And V2 is we're given 300 milliliters. So we just want to solve for M2. And from here, all you want to do is take these two numbers times each other and then divide both sides by 300. And we get that M2 is equal to, let's see here. Where did I put? Sorry, I've lost my answer key. M2 is equal to 0.336 molar. So that would be the concentration of the final solution. Now, one thing to note here is that our molarity equation is supposed to be in liters, but notice how we were able to perform this calculation using milliliters. Now, just a word of caution, you can use milliliters or liters in the dilution equations. Just make sure you use the same on both sides. So if you use milliliters over here, you have to also use milliliters on the right. What questions do you have on the dilution problem? Okay, let's continue on then. And I have another problem here regarding molarity. So I'm going to do part of these and then I'll let you guys have a shot at this as well. So number 5 says, which solution has the highest number of potassium ions? And it gives us 3 solutions, and each one that it's given has some volume and a molarity attached to it. And there's 3 cases, and so this is saying which of these 3 cases, case 1, case 2, case 3, has the most potassium atoms in it. So how can we relate our concentration of a solution to the number of atoms? Well, again, this we want to use the molarity equation. So we're going to use M is equal to moles divided by liters. Now, if we can get the moles, we know moles is related directly to the number of atoms present. So let's take this and solve for moles. Now, moles would be equal to M times L. So the molarity times liters, just rearranging this equation. So if we wanted to find out the number of moles of potassium in this solution, we take the molarity, 0.20, times the liters, so that's 5 liters, isn't it? Times 5 liters, and that will give us 0. No, that's 1.0, isn't it? It'll give us 1.0 moles of KCl. Now we have moles of KCl, and but we're not looking for moles of KCl, we're looking for moles of individual potassiums. Now we have to times this number by 1. I know that's kind of redundant, but the number of potassiums in KCl is 1, but it's not 1 in these other cases. Notice here there's 2 potassiums and here there's 3. So in this case we have to multiply this number by 1 and we get 1.0 moles of potassium. Now what you're going to have to do for the second and third cases is follow the same process to figure out how many moles of potassium are in each one. And if we can find the moles of potassium in each one, that will tell us which one has the most potassium atoms. So why don't you give this one a shot for the next minute or two, and then let me know what questions you have as you're working. Okay, let's continue on with number 5. So the same thing for each of these. We're going to take the molarity times the liters, and that's going to give us the moles. So let me just write that again here. So the moles is going to be equal to molarity times liters. So that's going to be 0.15 molar times 6 liters. And that's going to give us, let's see here, that will give us 0.9 moles of K2 CrO4. So notice whenever you do these calculations, you're always going to get the moles of this substance, not the potassium. So once again, to get the potassium, we're going to have to multiply this by 2. Why times 2? Well, because there's 2 potassiums in each K2CrO4. So this will give us 1.8 moles of potassium. And lastly, moving on to potassium phosphate. So moles is equal to molarity times liters. So the molarity of 0.08 times 8 liters, and that will give us 0.64 moles of K3PO4. Now, once again, this one here has 3 potassiums for each K3PO4. So this one we have to times by 3. And this will result in 1.92 moles of potassium. So we can now compare and see which one of these has the most potassium atoms. Now you just have to look at which one has the most moles of potassium. The first one has 1 mole, the second has 1.8 moles, and the last one, which is the answer, has 1.92 moles of potassium. So this one has the highest number of potassium atoms. Now, who can tell me, why do I not need to figure out the actual number of atoms? Why can I get the answer just from the number of moles?
Can you say that again?
Yeah, so the question was asking for the highest number of potassium atoms. We just found moles. Why can we still get the right answer from just finding moles, not atoms? Does anyone know?
Because you would use Avogadro's number, and that's the same.
Right, yeah, exactly. So Molly said you'd use Avogadro's number. So you could go to atoms if you want, but you would just be timesing by 6.02 times 10 to the 23rd for each one. So it would be like multiplying each number by the same thing. So if you want to multiply by Avogadro's, you're going to get the same answer, but it's a completely unnecessary step. What other questions do you have on number 5?
So if we were asked like to find it in atoms or in like any other form, we would just follow that little like conversion box thing with like the things in the Avogadro, all that stuff.
Yes, yep, that's exactly correct, Faith. So you
Thank you.
use this to get your moles, and then you just do what you're used to, the regular old stoichiometry. Yep, good question. Okay, let's move on and discuss electrolytes and strong acids and bases. Okay, so we will just kind of go through and discuss this one together. So there are 3 types of electrolytes here. There's strong electrolytes, weak electrolytes, and non-electrolytes. And these are differentiated from one another based on their dissociation. Now, what is dissociation? So let's say you took NaCl, so this is table salt here, and you are going to put it in a container with water. Should probably draw one bigger. So just imagine you're in your kitchen. When you put table salt in water, it no longer stays as Na and Cl. It dissociates or breaks up into sodium and chloride ions. This is water here. Now, when you take it out of the water and you evaporate all the water off, it'll turn back into NaCl. But as long as it's present within the water, we call this dissociation. Now, this is different from dissolving. Dissociation means that the atoms are literally pulling apart from one another when they're in the water. Now, this is how we differentiate different types of electrolytes is, do they do this dissociation process? Now, for strong electrolytes, we say strong electrolytes, these dissociate completely. In other words, when you put them in the water, they're going to completely separate from one another and become separate ions in the water. And these will conduct electricity. What does conduct mean? Conduct means it allows electricity to flow through. So when you get, they say don't swim in like a swimming pool when it's, or you might get, let's say, that's not a good example. Let's say you're in your bathroom and you don't want to drop your hair dryer in the water because the water can shock you. Well, it's not actually the water that is allowing electricity to pass. It is the electrolytes that are dissolved in the water that allow the electricity to pass. That won't happen in pure water. So the strong electrolytes will conduct electricity, will allow it to pass. Now these would be, these are going to be soluble ionic compounds. Zoom in a little bit more. Soluble ionic compounds, and we'll talk about solubility on Wednesday. It's going to be strong acids, and strong bases. And my mouse battery's dying. So we're going to talk about strong acids and bases momentarily in question number 7. So what strong electrolytes are compounds that are soluble ionic compounds, strong acids, and strong bases. Now, on the other end of the spectrum is a non-electrolyte. Now, a non-electrolyte is something that does not dissociate. So, and these also do not, they don't conduct electricity. Now, these are, these would be molecular compounds. And these include organic molecules. My mouse battery is like dying when I can go like this. Okay, there we go. Organic molecules. Now, organic molecules are molecular compounds, but something like gasoline you can think of, or sugar. Now, I'm going to draw a little picture here. Imagine you took sugar, which is like C6H20 or something like that. So it's carbon and hydrogen. It is a molecular compound. When you put this in the water, it is still C6H20. I don't know exactly what it is, C6H20 or what, but what I'm trying to say is it doesn't break up into pieces. Your sugar is still sugar when you put it in the water. Now, it's dissolved in the water, but it's not dissociated. Now, dissociated means it has to be broken up into pieces. So if things do not break up into pieces, if they don't dissociate, we call those non-electrolytes. So we have strong electrolytes, non-electrolytes, and then the middle ground we have weak electrolytes. So weak electrolytes are compounds dissociate partially. So this is something that some of them break up and some stay together. And these, they conduct electricity, but they conduct it poorly. So I'm just say poorly conduct. So they poorly conduct. It'll allow some electricity, but not very much. And these compounds are well, what do I say? So they're acids and bases that are not strong. So again, this all relies on you understanding what strong acids and bases are. And we're going to talk about that just a second here with question number 7. So to review, we have strong electrolytes that dissociate completely, weak electrolytes dissociate partially, and non-electrolytes do not dissociate. What questions do you have for me before we discuss strong acids and bases? Okay, let's discuss strong acids and bases then. Okay, so strong acids I'm going to do in red, and then the bases we'll do in blue. So strong acids, now just to review, an acid is when you have an H attached to the beginning of your compound. So there's a list of these that were provided in the notes, although it's not a total list. So I'm going to list out just the strong acids here from the notes, and then some ones from previous semesters also. So that'd be HCl, HBr, HNO3, oops, HCl, HBr, HNO3, H2SO4, and so these are the ones from the notes this year, but there are some more common ones that I want to mention just so that you have them on your paper. So the other ones that I would recommend writing down, and I'll write these kind of in a different color. So HCl, HClO4, HI, hydroiodic acid, and there might be one other you should write down. Let's see, 1, 2, 3, 4, 5, 6. Okay, that should be good enough. I don't think you're going to see any other ones in this class. These ones come straight out of your notes, and then the perchloric and hydroiodic acid, those are common ones we use in previous semesters also. So just write those down and keep those in mind, and we'll do an example problems with them in just a sec. Now the strong bases, so the base is when you attach a hydroxide on the end, or an OH. So I'm just going to list these ones out also. So lithium hydroxide, sodium hydroxide, potassium hydroxide, let's see, rubidium hydroxide, cesium hydroxide. So these are the metals from the first column on the periodic table. And then some other ones are from the second column, which would be calcium hydroxide. And since calcium has a 2+, there are 2 hydroxides. Strontium hydroxide and barium hydroxide. So this list, I mean, you're going to see slightly different lists everywhere you look, but I think this should be enough for you to do your homework problems. So, and we'll do a couple examples here, but what you need to think of is, just going back up to a previous problem, is we want to find out what type of electrolyte it is. And to find that out, we need to know what type of acid or base it is. So is it a strong acid? And you know that because it's on this list. Otherwise, it would be a weak acid. Same thing with the bases. Is it a base? Yes. Is it a strong base? Well, you have to look at your list for that. So we're going to do some example problems in just a sec, but before that, I want to stop and ask, what questions do you have so far? Okay, let's do some example problems. I know this is an overload of information, you guys, but let's try to do some examples here. And hopefully you have these written down. If not, I can always scroll back up. Now, here's a type of problem that they could ask you. Number 8 says, for the following, determine the type of electrolyte. Does it have full, partial, or no dissociation? And if it dissociates, break them into its component ions. So let's do one example together, and then I'll let you guys do a couple. So HClO4. What type of compound is this? Who knows what type of compound HClO4 is?
A strong acid.
Okay, so Sarah said a strong acid. Nice. So, and you knew it was a strong acid because it was on our list of strong acids. So another way to tell it's an acid is whenever you have this H on the front. So the H on the front equals acid. There are some exceptions to that, but for the most part, if you see an H on the beginning, you can assume that's an acid, at least in this class. So this is an acid. Particularly, it's a strong acid because it's on our list of strong acids. So what does that mean? What type of electrolyte is it? Well, let's go. Yeah, go ahead.
I think isn't it a strong electrolyte?
And how did you know it was a strong electrolyte, Megan?
Because when we did like defining them, the examples were the soluble ionic compounds and the strong acids and bases.
Exactly, yes. So we're going back up to our definition. Strong electrolytes include the strong acids. Therefore, we come down here and we say this one is a strong electrolyte. Very good. Okay, now part 2 says, what type of dissociation does it have? Well, same thing like Megan says, we can just look at the definition. We know strong electrolytes have full dissociation. So this or complete. So this HClO4 is gonna break up into its 2 component ions. So what would this look like? This would look like you had HClO3 or HClO4. And when you put this in water, it's going to break into H+, which is the hydrogen ion, and ClO4, which is the minus ion. So this is going to dissociate into H+ and ClO4-. What questions do you have about this process of answering these questions? Okay, why don't I give you guys a couple minutes and try to work through some of these next problems and let me know what questions you have. All right, let's continue working on these. I know I didn't give you guys that much time, but just because session's over at 5:20, I want to get you guys at least a couple more of these. And then the ones we don't finish, we can finish those on Wednesday. So CaCl2, this would be an ionic compound. And we know that because it's calcium is a metal and chlorine is a nonmetal, therefore it's ionic. Now, again, I mentioned we haven't talked about solubility yet, so let's just assume for now this one is soluble. And we'll discuss solubility on Wednesday. I just don't want to overload you guys today. So we have an ionic compound, a soluble ionic compound. That would be a strong electrolyte. So strong electrolyte. So soluble ionic compound, strong electrolyte, that means it has a full dissociation. Or in other words, it's going to completely break up into its ions. So we have CaCl2, and this is going to dissociate into calcium 2+ and 2 chlorine ions. Now, notice that the chlorines don't stay together. They break up as well. It's completely dissociating. Everything is breaking up into its own pieces. Okay, moving on, part C, CH3COOH. Does anyone know what this is?
Is it vinegar?
Yes, it is. Very good, Molly. This is vinegar, or the technical name is acetic acid, which is CH3COO minus, which is acetate, and then you attach an H on the end, and this becomes acetic acid. Now, please take a note of this somewhere. This is such a common, I'm going to just tell you right now, it's a weak electrolyte, but it's a very common one for them to ask. And one of the reasons is because the hydrogen here for the acid is on the end. Usually it's on the beginning, but in this case, it's on the end. So in this case, we have an acid. It's acetic acid, also called vinegar. And we have to wonder, is it a strong acid or not? Well, let's go up here. It's not on the strong acids list. Therefore, we have a weak acid. So we have a weak acid. Now, the weak acids from our definition were weak electrolytes, or acids and bases that are not on the strong list. So this is a weak electrolyte. This means weak electrolytes will have partial dissociation. So some of these are going to break up and some will stay together. Now the way we notate this is we have a CH3COOH, which is acetate, and we want to say partial, so we do a double arrow like this, going both ways. So CH3COO minus, that's the acetate plus the H+ ion. Now this double arrow here just signifies that it's dissociating, but it's not completely dissociating. Some of them are going to stay together as acetic acid. Okay, and let's do one more and then we'll call it for today. So C3H8. So this is a molecular compound. And we know that because carbon is a nonmetal, hydrogen is a nonmetal, therefore we have a molecular compound. Now molecular compounds are non-electrolytes. And therefore we know that non-electrolytes do not dissociate. And because it doesn't dissociate, we don't have to draw any of the chemical formula for dissociation. Okay, we are coming to the end of the session. I hope this gives you a little bit of understanding of electrolytes and strong acids and how to use them. We'll pick up here on Wednesday at 4:30. So we'll see you guys then. If you have any questions, feel free to hang out for the next few minutes and I can help you. Otherwise, have a good rest of your day.